So 8 bits, a byte is 8 bits. Something like an old Nintendo might have had an 8-bit graphics capability in it, meaning that it might be able to display from a palette of 256 different colors on the screen. And it could be that the resolution of the screen was limited to 256 pixels wide or something like that. The old Ataris before that had an even lousier video card in it. Not 8 bytes, maybe 4 bytes. I don't really know. Or not bytes, bits. So let's do the old Atari 2600 being 4 bits, 16. You could have at most on the screen 16 different colors. Some programmers were clever enough to hack the programming in such a way as to be able to generate more by either rapidly flickering between 2 colors or doing other programming hacks. But in general, you can only have one of 16 different colors on the screen at the same time. And the pixels were real big, you know, they're really blocky looking. So there's a direct relationship between the number of bits that your processor supports in one gulp and the capabilities of the machine. So a lot of machines invented like in the 60s had an 8-bit word size, meaning that the processor could chew up numbers of 8 bits at a time. And actually a lot of them had larger than that, because if you're the government and you can spend a huge amount of money, you could ask IBM to put in more vacuum tubes or whatever it would take to, you know, have a 10-bit or a 16-bit word size or whatever. Okay, so your Nintendo, 8 bits, then you buy your Super NES or your Genesis, and what was the big deal about them? 16 bits. Maximum number that a 16-bit value can contain is 65536. I just happen to have that memorized. So they had much broader color palettes. The games looked, you know, tons better on the Super Nintendo or the Genesis than they did on your old regular one. And things like Pac-Man and Space Invaders and stuff like that, all in the original, you know, arcades, were, you know, probably done on 8-bit architecture as well. So they didn't have a lot of colors available to them. And then, you know, then better things came out, and the, you know, the appearance of those games looked better as well. You know, usually far better than the home stuff. It wasn't until the home computer got really good, you know, and then you had your PlayStations and stuff where your home video games kind of outstripped anything that you could have in arcades, and so people basically stopped going to arcades. So then let's find out what this formula is for doing that. What this is 2 to the power of the number of bits, where x, 2 to the power of x, where x equals the number of bits in the architecture. I'm just going to use Google as my calculator. 2 to the power of 8. So 1 byte can hold 256 different possible values, 0 all the way up to 255. 16 bits, 2 to the power of 16 is 65536. The moving from a 16-bit architecture to a 32-bit architecture back in the 90s was a big deal, because you could address vastly larger amounts of memory. If you look at that, that might look kind of familiar. I believe that's 4 billion. For a long time, computers were limited to 4 gigabytes. Giga meaning billion. And when I say computers, I mean the kind that you buy at home, not, you know, the Cray computers or whatever, you know, that cost millions of dollars. And that's because their memory address scheme supported 32 bits, excuse me. Then what was the big change? From 16 to 32 bits, the newer versions of the Intel chips and stuff like that, even larger. So 2 to the power of 64 is just astronomical. Theoretically, something with a 64-bit addressing scheme, what is that? You know, 1.8 super quintillion. Yeah. You could put a lot of memory. There's still a limit in there, you know, but theoretically, a 64-bit addressing scheme is going to be able to hold a lot of memory. So I don't know when that's going to be exceeded, when they're going to need a addressing scheme that's larger than 64 bytes. Excuse me, 64 bits. Keep flipping those. Where else does this matter besides the number of colors available to the video card or the amount of bytes that can be addressed by the chip? The variables in a programming language are often limited to a certain number of bits, matching some kind of hardware architecture. They've all been stamped out, set in iron now by standards. IEEE standard 9 point whatever is a standard size for a integer or a floating point, and it'll be stored in this number of bits, that number of bits. Typically, in this language and in C++ and stuff like that, an integer is a 32-bit data type, whereas what's known as a long, which is a bigger integer, is a 64-bit data type. Why does that matter? Well, a 32 bits, I didn't even type it here. So 32 bits can go up to like 4 billion. Is that what we just decided? We have to divide that by 2 to get the largest positive value it can support, because numbers actually only use all but one of the bits available to them. Why? Because you have to have some way to indicate negative numbers. 0 up to 255, that's great, but what if your number needed to be negative 16? How do you represent negative 16 if all you got is 0 to 1, to 255? So they use the first bit as what's known as a sign bit. So that's not really available for the magnitude of it. It controls whether the number is positive or negative. So in real world terms, that means that an integer can go up to about 2 billion. So equals plus or minus 2 billion. A little bit larger, but if your number needs to be larger than 2 billion, you're not going to want to store it in an integer. The debt of the United States. Not a 32-bit number, right? It's in the trillions. You'd have to store it in a long. A 64-bit data type we saw as being huge, whatever it was. You know, 1.8 to the power of 19, you divide that by 2 to account for the fact that you only have half as many. All right, so it's 9 super gazillion, whatever, you know. I don't know what 2 to the power of 18 is, but so anyways, 9 times 10 to the 18. Or can we go all scientific notation and just say that that's 9e to the 18, and we understand what that means, a 9 followed by 18 zeros? Obviously a much larger value. If you need numbers larger than that, there are data types that will support those still. Best way to do that is just to switch to a floating point type. Why? Because floating points support exponents. You know, even if you just had a very few little bits involved, you could say 2 times 10 to the power of 400 or whatever. That didn't take very many bits to show. That's probably less than a 16-bit value there. But, you know, that's a 2 followed by 400 zeros. Much larger number than even a long. So any floating point type will store a larger value than the largest integer type. So if you need to store big numbers, use a floating point type. The drawback to using floating point types is you can get rounding errors. It's not exactly precise. You'd think it'd be precise, but it's not. We can demonstrate that by dividing a number by like 7 and then multiplying it by 7, and it won't be what it was. Yeah. It'll be off just by a little bit of rounding error, because floating point math works different than integer math. So integers are very precise. Floating points, they look precise, but they're limited in their precision. One floating point type has, like, I believe, 8 points of precision. So you could have like a decimal followed by 8 numbers. And if you need to be more precise than that, like if you really wanted to use for all 400 spaces, can't do that. You can only hold like the first 8 numbers, and then the rest of them would be assumed to be 0. So not super precise. Now where are we going with this? How to count in binary. It's going to seem real familiar to some of y'all. We're driving in a car. It's we go past mile marker 1, mile marker 2, mile marker 3. We stop passing mile markers, but we still keep driving. And then what happens to our odometer? It rolls over, right? So we get 10. Technically, what has happened, or if we're going to drill way down into it, we have exceeded the largest digit that our counting system supports. So we're not counting in binary here. This is how to count in decimal. Decimal meaning 10. We have 10 different digits. 0 is a digit. You know, you ask a kid to count, they're going to start counting, you know, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. But by the time you get to 10, you've got those 2 digits. So the accurate way of counting would be 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. And then, oh, well. So I did that wrong. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. And so 0 through 9 is 10 digits. So we exceeded the maximum value in our counting system. So we went back to the beginning. We went from 9 back to 0, and we added 1 to the next column, incremented the next column. And then we kept repeating the process, right? And eventually, you know, you're at 1999. If you go another mile, it exceeded the counting system, so that becomes a 0. What happens? Well, we have to increment the next one by 1. So that one flips from 9 to 0. And then add 1 to the next column, and so on. And you all know how odometers work, and you've understood counting, you know, since, you know, first grade or whatever, whenever you learned about numbers larger than 9. That's how you count in binary, in decimal, using that many digits. Binary doesn't have 10 digits. It's bits. All it's got are 0s and 1s. So our car odometer is going to look a little bit different. We drive 1 mile. Now we drive another mile. Uh-oh. All we have is 0 and 1. So we roll this one back over to 0, and we add 1 to the next column. Okay, that's cool. Now we drive another mile. And then this is just like when we're at 99. We drive another mile. Well, we need to add 1 to that, but we've exceeded our limit, so that becomes a 0. In that place. So let's add a 1 to the next column. Well, it's already at 1 too. It can't go any higher. So that becomes a 0. And it rolls over like that. That makes sense? So we keep driving, and I'm not going to do the rollover spiel anymore. But have I goofed? Let's see. There should be 8 possible choices. Why is that? Because 2 to the power of 3, 2 to the power of number of bits, is equal to 8. So, since I had a 3-bit number, okay, so there's 8 values. All right, and then apparently if our car only has 3 bits, once you drive up past 111, it's going to go back to 000. Do you remember when cars like had limited odometers and you could get really psyched up because, you know, you went over 99,000 miles in it, and you know, you see all the zeros come back up. Nowadays, odometers, you know, go up to the millions or whatever because we drive our cars a lot longer than we used to. So anyways, if we look at these, this place in this numbering system, in the decimal numbering system, is what's known as the ones place. That's the tens place, and that's the hundreds place. So we have the hundreds place, the tens place, and the ones place, which is really 10 to the power of 2, right? 10 to the power of 1, and 10 to the power of 0. And if my marker worked, I would show y'all why anything to the power of 0 is 1, with the possible exception of 0 to the power of 0. I don't know what that would be. But any number to the power of 0 is 1. So if we were counting in something that was base 8, people used to use base 8. They called it octal. It would have 3 different places as well. It would have 8 to the power of 2. It would have 8 to the power of 1. And then it would have 8 to the power of 0. So it would still have a 1's column, but it wouldn't have a 10's column. It would have an 8's column. And it wouldn't have a 100's column. It would have a 8 times 8, which is a 64th column. I'm going to erase that because we're not concerned with octal. But now that we're dealing with binary, we have 2 to the power of 2, 2 to the power of 1, and 2 to the power of 0. So what's 2 to the power of 2? 4. And then 2 to the power of 1 is 2. And then 2 to the power of 0 is 1. So if we pick any number here, let's just number them consecutively in decimal. That's a 1, that's a 2, that's a 3, 4, 5, 6, 7. No, that's not a 1. Somebody should have slapped me. 0, 1, 2, 3, 4, 5, 6, and then 7. 7 is the largest number that can be displayed in 3 bits. And you said, but 8 was the largest number. No, you have 8 different possible values, but you have to count for 0 in that. So 8 minus 1 is 7 is the largest. Why does 111 equal 7? Well, it's because it's equal to 1 times 2 to the power of 2 plus 1 times 2 to the power of 1 plus 1 times 2 to the power of 0. My brain just broke and I can't find the power anymore. Okay, there we go. In other words, 1 times 4, right? So if we're trying to translate the number 111, we could say that that's the 4's column, that's the 2's column, that's the 1 column. This is equal to 1 times 4 plus 1 times 2 plus 1 times 1. 4 plus 2 is 6, plus 1 is 7. If you wanted to shorten it and not add all those 1's, you could just say it's 4 plus 2 plus 1. Okay, so 3-bit numbers are so easy that you could memorize them really quick. Let's do 4-bit numbers instead. If you have a 4-bit number, not only do you have 2 to the power of 0, 2 to the power of 1, 2 to the power of 2, but you have 2 to the power of 3. The first digit is a 3. So counting from 0 all the way up to 1, what is 2 to the power of 3? Well, the easy way to do it is just to double each time. If that's the 1, that's the 2, that's the 4, what do you think the next one's going to be? 8, and then 16, and then 32, and so on. So we have 16, 8, 4, 2, and 1. Can I type? 8, 4, 2, and 1. So if we want to find out what 1111 is, well, it's 1, 8 plus 1, 4 plus 1, 2. So why did I type a 2 there? And plus a 1, right? And if we add all those together, 8 plus 4 is 12, 13, 14, 15. So in a 4-bit addressing scheme, the largest integer that could be held in it is 15. What if we have this number, 1010? What does that equal to? Just tell me the values starting like with an 8. It's equal to an 8. Are there any 4s in it? No. Nope. Plus a 2. So the 1010 is equal to 10. All right, that's about time for us to actually go. What am I doing on Facebook? Jeez. Alrighty. So I'm going to move this pending in class up to due in class. So if you refresh your Dropbox, What's the difference between do in class and in class do? Good question. All right, refresh your Dropbox again. You'll see the second in-class assignment called Binary and Hex. Should be a Word doc. And those of y'all who did this in a previous class, I apologize that it's very, very, very similar. But we're going to do it anyways. Okay. So, if 1011 is equal to an 8 and no 4s, plus a 2, plus a 1, an 8 plus a 2 plus a 1 is an 11. Fill in the next 4 slots. And if it says that it's read-only, you can change it by clicking under View or something like that, one of the menu choices up at the top. Alrighty, some of y'all have stopped typing, some of y'all not. Give you another 30 seconds or whatever. Actually, I know it takes longer to type this than that. Typing the answer would be really fast, right? But 4 plus 2. Let's just work on them together, though. What's this first one? In fact, I just said it. If I was going to read this one aloud, that's, and let's skip the 1 times business. What's the first non-zero digit in here?
4.
It's a 4, so it's a 4 plus a 2 is equal to a 6. How about that one? 8 plus 4 plus 1, that's 13. Guess what? All zeros is 0. That's the gimme. And then that one we've already done before. What are its components? 8 plus 4 plus 2 plus 1. Let's tack on one more 1 just to be challenging. So now it's got 5 ones in a row. So not only does it have a 1, 2, 4, and an 8, what would the last one be? We have to tack on 16. So I believe that's 31. 16 plus 8 is 24, 28, 29, 30, 31. Alrighty. The next one, convert the following binary sequences to hex. Well, that'd be a lot easier if we talked about what hex is. Going back to here, if decimal are the numbers 0 to 9, and binaries are the numbers 0 and 1, decimal has 10 different possibilities, 0 to 9. Hexadecimal has 16. Hex meaning 6, dec meaning 10. So it's got 10 different possibilities. So it's got 0 through 9, but then we have some more digits that we need to fill in. And obviously the Russians used different letters than we did, so their hexadecimal looked quite different than ours. We like English. So we had to pick 6 letters in order to indicate the additional numbers, rather than just make up, like an upside down U and a, X with a crossover. They could have done anything, but A through F. If you count A, B, C, D, E, F, those are 6 additional values that we can treat as digits, giving us our total 16. And I spelled that wrong. It's not hexadecimal, it's hexadecimal. Let's give some more technical terms of these. Rather than binary, I can also call that base 2. Decimal can be called base 10. And hexadecimal can be called base 16. It works the same way. Now the values get very large very quickly, so I'm not going to focus too much on them. But if you think of it as being, say we have 6 hex digits. 103E. Well, where'd that E come from? Because we've got to count in sequence. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. We haven't maxed out our system, though. We still have more digits, so we can keep going. A, B, C, D, E, F. Now we've maxed it out. We've hit the highest digit that hexadecimal supports. So we reset that one back to a 0, and we add 1 to the next column. And then 11, 12, 13, 14, 15, 16, 17, 18, 19. It's not 20. What is it? What's one higher than 19 in hexadecimal? What happens to the 9? We just keep counting, right? Because it's 1 through 9 followed by A through F. So 1A, 1B, 1C, 1D, 1E, 1F, and so on, all the way up to FF. That's the largest that 2 hexadecimal digits can add up to, is FF. Well, what is FF in decimal? You know, we already found out what 1, 1 is in binary, or 1, 1, 1, 1, or whatever. So FF, what are the powers of? If this is 16 to the power of 0, what is that lastmost column? It's still the ones place, right? 16 to the power of 0, or anything to the power of 0 is a ones column. So that's a ones column. But then what's this one? It's 16 to the power of 1. Which is what? It's 16. And then the next one, 16 to the power of 2. What's that? It's 256. Why do I know? Because I've done this before. 16 to the power of 3. Honestly, I don't remember. Is it 4096? Let's go look. Google is my calculator. 16 to the power of 3 is 496. So in decimal, we have a ones place, a tens place, a hundreds place, and a thousands place. In hexadecimal, the numbers get much larger very quickly. Just like in binary, the numbers get large much more slowly. They just double. 1, 2, 4, 8. So by having more possible values per digit, you can express larger numbers in fewer digits. It takes a lot more digits, zeros and ones, to express the number 32 in binary than it does in decimal. So now that we have our powers of 2 figured out, let's figure out what this number is. 103E. Okay, for us to figure that out, we really need to kind of set up an equivalency table so that we don't just have to keep remembering what an E is or whatever. So it's 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. What's next? Not 10. A, B, C, D, E, and F. But let's go ahead and give them the equivalent decimal values as well. 0, 1, 2. Why didn't I hit the tab key? That would have been better. 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. No, 15. Okay, so say we have the number 1A 3E, and we want to convert that to decimal. Convert 1A 3E, and I'm going to indicate that it's hexadecimal by using a parentheses. That means base 16. To base 10. That's how I'm going to indicate base 10 or decimal. Okay, well, this is 1 times 496. 1 times 4096. Plus, well, what is an A? An A is a 10. So it's 10 times 256. See how this is working? Plus 3 times what? I think I heard somebody say 14. If this is 1 times 496 and this is 10 times 256, then this is going to be 3 times what? Don't make me highlight it. 16. All right. And then what's the last column? Plus E, which is 14. Like you said, times what? Times 1. Okay. And then I'd actually have to type I'd have to whip out a calculator and do that. Again, I'm going to cheat. Google, tell me what the answer is. Okay, it's equal to that number. I don't think I'm going to ask you to do that very often. That's kind of tedious. But why did they invent hexadecimal in the first place? Well, because looking at a page full of zeros and ones would be really annoying. Looking at decimal numbers is great and all that, but you can hit a higher information density by using hexadecimal. And I'll kind of show you what I mean after a while about that. But let's figure out the binary versions of these. If I'm going to count binary, that's a 0, that's a 1, what's next in binary? We travel down the road, it is a 0010 followed by a 0011 followed by 0100, 0101, 0110, 0111. If I was doing this in Excel, I'd just copy, paste it, and change the leading numbers because we roll back over to 1,000. I hope I do this right because I don't want to have to make any corrections. So that is our handy dandy hex, decimal, binary conversion chart. Pretend it's spaced out appropriately. What do I mean by that? If I give you this number, 1A3E, and I want you to convert it to binary, to base 2, you can do that real easily if you have this kind of chart. Why? Okay, so what's a 1 hex? Let's drag this over here. What is a 1 in hex? What is it in binary? It's right there, guys. We just do a simple lookup. 1 is 0001. What is an A? 1010. What's a 3? 0011. And what is a E? 1110. So 4 bits can be converted into 2 hexadecimal digits really cleanly. And I guess we have time to compare expressing decimal and hexadecimal to mean the same thing. We're going to go the other way now. We're going to take a series of binary digits and convert them to hex. And I'm just going to make them up at random. Okay, so let's break them up into groups of 4. What is 1001, the hexadecimal equivalent of it? What's next? 1100. C, yep. What's 0100? That's a 4. And then lastly 1011. B, okay. If we were going to express this in decimal rather than hexadecimal, it'd look a little bit different. Same numbers, but use the decimal column now. What's 1001 in decimal? 1001 is, it's still a 9. How about the 1100? It's a 12. How about the 0100? It's a 4 still. And how about 1011? It's 11. We can't cleanly express these clusters of 4 into single digits. if you're displaying in base 10. So you wind up sticking zeros in front of everything, you know, in order to space it out properly. So in order to display 4-bit numbers as base 10, as a sequence of base 10, you wind up using twice as many spaces on the screen. So that's maybe one possible explanation for using hexadecimal rather than decimal. You can directly map in your head, once you learn all these corresponding things, that a 9C4B is equal to these 0, 0, 0s. That, all these zeros and ones. Go back to your Word document now. Convert the following binary sequences to hex. Fill in the question mark spaces if you are already done. Can I get rid of those paragraph symbols, por favor? Alrighty. It's far easier if you have a hexadecimal chart in front of you, like we were just using. So I'm going to bring up the hexadecimal chart. I'm sorry it's not tabbed out nicely. I'm going to tab it out nicely. Y'all can already start working on these. You don't need me to step you through them, but I'll do the first one. And then let's... Okay, so obviously 0, 0, 0, 0 is 0 in hex. What about 0, 1, 1, 0? Well, I look it up. 0, 1, 1, 0 is a 6, so I'm going to fill in a 6 there. You do the next two while I finish hitting tabs on everything. All right, so what's that one? That 1110. B? All righty. E. Yeah. That's what you're saying, and I can't hear you because I'm deaf. All right, and then 0101. 5. All right. And then all of that, that'd be a 1. Right? Okay. Then do the reverse. A B is a 1011. A D is a, yeah, 1101. A 7, 0111. An 8, 1000. A 0, I don't know why I have 0 in there, but that's pretty easy. 0, 0, 0, 0. And an F, all ones. All right, I don't think there's any more homework in here. Oh, there is on the next page. I'm getting tired of talking about numbers. On the other hand, if we miss Tuesday, I'm still getting tired of talking about numbers. Scroll down to page 3 of 9. This is just doing what we were doing in class earlier. If we're going to convert 1010 to decimal, that means it's 18, no 4s, 12, and no 1s. So 8 plus 2 is a 10. And 8 plus 1 is 9. Are there any of these that are not done? I think you already have the idea, and not finding a place that's not already filled in. All right, then why do we stop there? I probably had better put it on a quiz to burn it into your brain, and I know that half of y'all already know it. So we'll stop there with that. Just save this and upload it to the Dropbox, same Dropbox where you downloaded it from. Sometimes I forget to stop and ask if all that made sense. That made sense, guys? If it didn't make sense, wave your hand and I can blather another 10 minutes on it. And I don't mean that in a pejorative sense. I really can just talk about it as long as you need me to. So, chapter 1 of programming books are usually pretty cut and dry. They always start with what is a computer and stuff like that. Read chapter 1. It really only gets interesting towards the end. And I really shouldn't skip past the PowerPoint for it. So I'm going to go ahead and open it, but we're just going to fly through some of it. You know what a computer is. So a computer is something that consists of a CPU. All a CPU is a little box that manipulates zeros and ones to symbolize numbers. Everything to a computer is a number. But what about pictures? They're just sequences of numbers in a very specific format. What about songs? Well, MP3s are very specific forms of numbers that are translated as a sound. What about writing? Well, writing are a very specific series of numbers that are treated as text. So a CPU has main memory. What is main memory? It's those zeros and those ones broken up into clusters of 8. And modern computer would have like 4 gigabytes of them. It'd have 4 billion clusters of 8 bits, whatever. Even phones, have 1 or 2 billion bytes anymore. It's amazing what technology is. And then they have they need a storage device as well, because otherwise if you shut off your machine, you would lose everything that was in memory. So you need to have hard disks. Nobody uses hard disks anymore. Solid state drives, flash memory, that's what all of our phones use. So that data can be recorded permanently or semi-permanently, nothing is forever. So that when you load your machine back up, you can pull that data back in. You know what an input device is and what an output device is. Input devices feed stuff into the computer. Output devices take data from the computer and puts it on a screen or on a printer or down a fax modem or, whatever your output device is. Nowadays, things are more complex than this. Why is that? Everything has got two-way communication now. Your printer is communicating back to your computer. Every peripheral now is its own computer. Even keyboards, you have these things that'll flash all the lights or whatever, and they're reprogrammable, and you can rearrange the keys, and so everything is its own little pocket computer. So it's not as cut and dried anymore that a mouse is only an input device. If you had a mouse that was displaying alphanumeric text on it, then it's also an output device. Same with the keyboards. People make keyboards where every key on it, all the keycaps are just LCDs, so that you can completely change what keys are on it. So it could switch from being, an English keyboard to a Russian keyboard just by, running a program that would change all the keys. But anyways, but by and large, you know what input is, you know what output is. Then we step into something like fundamentals of programming. Algorithms. What is an algorithm? It's a sequence of steps you use to follow a problem. Baking a cake is a problem. Your algorithm is a recipe that you follow. If you want to calculate your miles per gallon, you need an algorithm. Miles per gallon means miles divided by gallon. So you drove 100 miles and you used up 4 gallons. 100 divided by 4 is 25 miles per gallon. That is the algorithm that you follow. A lot of what we do in programming is implementing algorithms, formulas. Now, I'm not going to teach y'all how to do pseudocode and flowcharting because I'm assuming that you've already had a class in which you did that. So, if you write source code, you're writing something that's in English-like text. A equals 3 plus B. If whatever, then do something, English-like words and mixed in with arithmetic symbols and punctuation and numbers, right? That's what we type in. But a computer doesn't know what that is, has no idea what that stuff is. It has to be turned in ultimately into binary code that can drive that CPU. And different languages get to that point in different states. If you're writing a C program or C++ program, what happens is you write some source code. A is equal to 3. B is equal to A plus 10. Print B. You know, you write those three statements, and then a compiler comes along and turns that stuff into machine code, into machine language, binary instructions. They're calling it object code. So it gets compiled into an executable. Or on a Mac, they're called .app files. You know, on Linux, I don't think they're called .exes, but whatever. They get turned into binary code that can then be fed directly to the CPU, and the CPU runs on it. And that's well and good. This makes very efficient code. It takes those English-like commands and turns it into zeros and ones that can be fed to the CPU as fast as possible code, unless you write an assembler, which I'm going to skip for now what that is. Unfortunately, it's very platform specific. If you write binary code that runs on an Intel system, you're not going to then be able to copy that onto your Android phone that's running an ARM chip, or something like that. And you're not going to be able to copy it onto to something running a Motorola chip or whatever, because they are expecting the machine code. Well, they're not expecting it. The necessary machine code is in a completely different format for those things. So you can't take an executable that was written on Windows and run it on your Mac without doing something special, running emulation software. And y'all probably know what emulation software is. You have some old, Nintendo games. You want to play it on your computer. You run an emulator that lets you take that old machine code and run it on your new one. Or, they make the PlayStations backwardly compatible. I don't really know if that's true. So you can play PlayStation 3 games on your PlayStation 4. It's running an emulator. Or if you want to run Windows software on a PC, there's an emulator for that. But that's the drawback of having something that is compiled. So what is object code? It's just a sequence of zeros and ones ultimately. And yeah, you could translate them into hexadecimal in order to, to represent it more succinctly, but it's not going to make any sense to you and me. And I know a lot of y'all have done this, but go to open your browser and type hex, H-E-X-E-D, hexed.it, hexed.it, like edit. There we're given all these zeros and ones, this hexadecimal display over here, and we get a little ASCII readout of what that means. And I'm not going to even bother talking about ASCII right now. That's another lecture. But let's load an executable file. Do open file, and then go out to the C directory, OSC:, and then go into some Windows directory and find some executable or DLL to upload. That's what machine code looks like. It's just all the zeros and ones that adds up to these hexadecimal values. You can see some English-like text here. This program cannot be run in DOS mode. Well, isn't that a legacy thing? So that's what object code is, also called machine language. Nobody writes object code anymore. Nobody runs machine language anymore. We're well beyond that. Say you want some code and you want it to run on Linux, and you want it to run on Mac, and you want it to run on your phone, if your phone has Java installed on it, which I don't think very many do. And you want to run it on Windows, Mac, Linux. You can't compile it down to object code, to machine language. So what happens instead is you write it in a form of language that supports a virtual machine, which is an emulator in effect. So you write some code and it gets compiled into an intermediate form called bytecode. And this is the way that C# works as well. Not C++. C++ goes straight to an executable. So your Java code is turned into an intermediate code that can then be put on any machine, and as long as you have an emulator a virtual machine that can read that and then turn it into, on the fly, the ones and zeros it needs to drive the computer, you're good to go. So when we write a Java program, behind the scenes, what's happening is, the first thing that happens is it gets compiled into bytecode, which is not zeros and ones. It actually looks kind of like, English, but it's way lower level. It's an assembler type language. It's not really readable to humans. And then the Java virtual machine, also known as the runtime engine, interprets that stuff, turns it into machine code that your CPU processes and displays stuff on screen. So the Java source code, the Java compiler turns it into bytecode. And then when the Java program is run, the virtual machine translates that bytecode to object code and it's run. And that happens every time you run a Java program. That's why you have to install Java on a machine in order to run a Java program. If you don't install Java, you're not going to be able to run that Java program. Servers that use Java programming on the server side rather than on the client side do have Java running, on their side. That way you don't have to be running Java in order to see what their code is coming up with. The history of Java. Read the textbook. I'll give you the really, really short version. Sun Microsystems thought that the next big thing was going to be programmable devices. Microwaves and fridges and all this stuff is going to be networked together, and thermostats and stuff like that. And eventually that kind of became true, right? You network them with Wi-Fi or whatever, but you have smart homes with thermostats or whatever. They thought that if they created a language that could run on any type of computer, it didn't get compiled down to an executable, then appliance makers would license it so that the same stuff that ran your car could run a microwave, could run a smart television, a desktop cable box, or TV top cable box, that kind of stuff. So their idea was, we make a language that gets compiled into the intermediate form, and then all we have to do is write that interpreter, that emulator, that lets that coffee pot or that fridge or that thermostat or whatever run it. So they came up with such a language. They expected to sell it to appliance manufacturers and cable TV companies, and everybody went, yeah, meh, whatever. But they figured out that if they put it on the PC, then you could make software that ran on multiple machines. And back then, there were an awful lot of Macs, not just 1% of the marketplace. Believe it or not, in the 80s and 90s, you'd have like 30% Macs for 100, especially in a corporate environment. 30% of them being one thing. And it was really nice to be able to write software that would run on both of them without changes. That's called portable. You write software that'll run on a whole bunch of different devices. It's portable. You don't have to change your program in order to run on one different kind of machine. And so they introduced it for the PCs to be used with web browsers, and so that then everything went off, like gangbusters. Java got an awful lot of publicity. So originally, Sun planned to use C++ for home appliances, but they realized that it's less than ideal. It's not portable. It has to be compiled for every different architecture, and you can't guarantee that your cars and your phones and your cable boxes are all going to have the same chip inside them. In fact, you can pretty much guarantee that they're not. So rather than write C++ software, they created a new language that was similar to C++, but had a lot of the wrinkles ironed out. They called it Oak because there was an oak tree outside. Yeah, whatever. Then somebody called it Java. That was a better name. All right, the history of Java. So web pages have to be portable because you want them to display on any device. What's the standard language used for web pages? Something called HTML. And then JavaScript. JavaScript and HTML make pretty interactive web pages. JavaScript wasn't originally part of the web, and so your web pages were very static. All you had was pictures and text and then links to other pages. So you could embed Java programs into a web page, into something called applets. Nowadays, nobody does that. Some people do it. You still have to install Java on your computer, right? But you can get pretty well with having it disabled. How many people run into sites where you absolutely have to have Java installed? Not many anymore. Although applets still play a significant role in Java's current success, I don't really know about that. Some of the other types of Java programs have surpassed applets in terms of popularity. Nowadays, if you are going to program in Java, you're not programming for the web. You're writing an application that'll run on an end user's machine, not just something that makes it, modifies the appearance of a web page. People use JavaScript for that. The relationship between JavaScript and Java, is one based on the other? Absolutely not. The people who invented JavaScript, a company known as Netscape, you may have used Netscape browsers when you were a kid, came up with a language, and Java had a big buzz about it, and so they just took the name Java and added script to it. I'm sure Sun wasn't happy about that, but apparently they got away with it because people still talk about JavaScript. By the way, Oracle has bought Sun, so now Java is maintained and licensed by Oracle, as it mentions here. Alrighty, computer ethics. Don't know why a programming book has to cover this, but let's hit it anyways. The 10 Commandments of Computer Ethics. Thou shalt not use a computer to harm other people, unless you're flying predator drones. Thou shalt not interfere with other people's computer work. Don't be a hacker. Thou shalt not snoop around in other people's computer files. This is getting kind of, I agree with all these, but thou shalt not use a computer to steal. No ransomware. What is ransomware? It's when your computer shuts down and it tells you you have to pay $10,000 in order to access your data. Usually it starts off saying, we have detected a virus and you must run this application to clean up the virus. And so you mistakenly click on a thing that says, please clean up my computer, because you don't know not to. And it encrypts your hard drive, and then you have to pay somebody to unencrypt it. Thou shalt not use a computer to bear false witness. That is silly enough, and I'm just going to skip the rest of this. Alrighty. Quiz questions. What is pseudocode? We didn't talk about pseudocode because I skipped it. But if you took fundamentals, you know what it is. It's not a programming language. It's just an English-like description. Add 1 to X. Stuff like that. You can write requirements in pseudocode, but then somebody has to actually go and turn it into programming code. So does it use precise computer syntax? Nah. Does it compile an object code? Nah, because it's not a precise syntax. Often used in writing an algorithm? Yeah, absolutely. You have to describe the algorithm. Here's how you calculate pi mathematically. That number pi had to be actually determined. It just didn't, fall from sky on a stone tablet. So there's an algorithm for calculating it. And it can be expressed in pseudocode, and then you give that pseudocode to somebody and they can write it in Python or Java or C or whatever language. Java programs can be embedded in web pages, and those are called applets. And the support for applets is dwindling markedly. A lot of people won't install Java on their computers because they think that there are security risks, and in some fair degree they're correct. So if they're embedded in web pages, they're not an application. It's certainly not an operating system. An Android phone is about the closest to any operating system that's based on Java, and it's not really either, but the applications are written in an offshoot of Java, and there was a big to-do between Google and Oracle over that, because Google cloned the Java language and put it on the phones without paying Oracle any licensing fees. And so Oracle wanted their money. Google said no, and Google won that one. They didn't have to pay Oracle for their offshoot of the Java language. And is that the last page of the quizzes? What? I didn't put this slide here. Delete that slide. What happens if you're caught working together on a homework project? We talked about that in the past. You get a 0 and it gets escalated to the dean. So none of these answers are right. Double secret probation. I like that one. If you submit homework 2 class periods late, what happens? Well, I have the sliding late penalty. I think we're about done with that. I'm lectured out. I can't come up with any more homework that I want to give you based on the idea of binary and hex. I will come up with a quiz on it, and I'll upload the quiz by next week, but then you're going to have a week to take it, so it's not going to be a big deal. Remember, no class on Tuesday, so I really should give you a homework assignment, but we haven't actually covered the specifics. Your homework assignment is to read Chapter 1 and then be done with it. Pardon me? Sometimes I give extra credit, but I don't know what I would assign to give. I haven't cooked one up. Let's go look what I have done in previous semesters. We're not ready to assign homework problems unless you already have previous experience, so I'm just going to hold off doing that. What you really need to do instead of reading Chapter 1 is to start Chapter 2. That's where the meat of the programming language starts kicking in. So read Chapter 2. If you don't have the book yet, read the Chapter 2 PowerPoints, and please have made significant progress in that by Thursday. No. Yes. Can you just use the PowerPoints? Yeah. Is it nice to have the book? Yeah, it's really nice to have the book. There's lots of code examples in there that aren't in the PowerPoints. I recommend you get the book. Notice that word recommend. All right? All right, so I'll see y'all in a week. We will actually be coding as of Thursday, so please read Chapter 2, or at least the Chapter 2 PowerPoint, which you can find in D2L.